Hi. What we have done up to now, let me show you. So we examined the combination circuit synthesis in general. Now we said we are going to find the canonical form synthesis, which is the same as the previous one, it might seem at the beginning, but it is not the same because we are talking about the minimal function synthesis. So canonical form synthesis do not have the minimum number of components in it. Therefore, we are introducing the minimal function synthesis here. So for this minimal function realization, we've got two methods. One of them is called Kuhn-McCluskey method. The other method is the Carnot-Map method. So those two methods, you're going to end up with the same result. But in some cases, one of them is a bit faster than the other one. Therefore, we are using these two methods. Apart from those two, there are some other methods. We're going to mention the name of these methods. Do not give the details of these methods. Now, this video is related with this how to find minimal function part of it. Kuhn-McCluskey method. So for this one, for also for the Carnot-Map, we are going to have some definition. We need some definitions. So this video is related with these definitions. So in this frame, we've got 1, 2, 3, 4, 5 subframes. So this video covers those frames. So let's go in details for those. Now, what are those? We're going to mention, we're going to define the minimal function, and a bit confusion definition is irreducible function. What's the difference between the irreducible and the minimal function? Which one do we have to choose? That will be explained. And we're going to introduce a new terminology which is called prime implicant. I'm going to say what this prime implicant is and how to find the prime implicants, and then the steps of the method will be examined in this video. So let's escape from here, move it down and put that in open board selection. Okay, here we are. So how we said we're going to, we already said that first canonical form, first canonical or second canonical forms, each of those canonical forms. So that is sum of products, that means and/or, and product of sums, that means or and. Type of realization we can find. Example, here you are. This is a function. For this first canonical form, we've got this expansion, first canonical form expansion, and/or expansion of product of sums expansion. For each product term, there is an AND gate here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And the fan-in for these AND gates is the number of variables, which is 3. So this is fan-in 3, 3 here, 3 here, 3 here, 3 here. And this fan-in of the OR gate is the number of product terms. 1, 2, 3, 4, 5. Fan-in here is 5. So altogether 5. So that is synthesis, isn't it? If a function given to me, I can write the first canonical form and find the corresponding circuit, which is this. So this is synthesis. Finish that. So similarly, I can write this canonical form and throw another circuit here. Now we are saying the efficiency is not good for this design. Why is that? Because we've got, I'll show you at the beginning, this g function here is equivalent to f function. This f function is equivalent to that g1 function. G1 function is equal to this UR. That is G1 function. So if you if you draw the circuit corresponding to this function, you've got this circuit. Since this F equivalent to G1, whatever this circuit does, this circuit also does the same thing. But the cost of this circuit is much less than this one. Why is that? Because you've got 5 AND gates here, you've got only 3 AND gates here. In here you've got fan-in for each AND gate 3, but in here fan-in for each AND gate is just 2. On the other hand, you've got one OR gate and another one OR gate in this one, but the fan-in of this OR gate is 5, while fan-in of this OR gate is just 3. So the efficiency is much higher in this design than this one. So look at, okay. Then how we can increase the efficiency? We need the definition of minimal function. What is minimal function? Minimal function is going to be, here it says, equivalent to the given function. It should be sum of product form, so there are two minimal functions that we can design. One for the sum of products form, the other one is product of sums form. So let's consider the sum of products form now. Equivalent to the original function, it should be sum of products form. Sum of product form function, the number of product terms should be minimal. Meaning in practice, number of AND gates are minimal. So these are minimal. And also OR gate fan-in is minimal. Because if these numbers and numbers minimal, then OR gate fan-in is minimal. Apart from that, the number of variables in each term is minimal. So that means these fan-in of these AND gates are minimal. So let me repeat it now. I mentioned mathematically a minimal function. I said this minimal function is going to have, first of all, it's going to be equivalent to the given function of the truth table. And then we said the number of product terms should be minimal. At the same time, the number of elements in each product term must be minimal. So what it means, this minimal function, if you draw the circuit which corresponding to this minimal function, is going to have minimal number of AND gates in it. Also, it's going to have the minimal number of inputs to these AND gates. That means fan-ins are going to be minimal. If the number of AND gates are minimal, then this OR gate fan-in is going to be minimal. So that means minimal function, minimal cost. Under the condition that is sum of product form. So if it is sum of product term, this is a constraint. Yani bir kısıtlama geliyor burada. This is a good constraint. Why is that? Because the level means, sum of product forms means two level. The first level product terms, the second sum term means AND gates, second level OR gate. So for this form, the cost is minimal. But There could be some other forms. Example is this one, for example. This G2 here is not in sum of products form because there is a mixture of product and sum here. So this represents tree-level realization. So realization of G2, for example, equivalent to F, has got 3 levels, but this has got 2 levels. But 3 level number of gates could be less than this number of gates. Okay, so in terms of cost related with the elements could be less for the high level circuits. So which one is better? I don't know. In which cases, there could be some cases I can accept this more than 2 levels included in a circuit, but consider only the cost of the gates. So you're going to, this is a new design. It's not the one that we are going to explain here. This is going to be another method. High level function realization. That is multiple level function realization is this one. We are not going to examine this one. We are going to examine this one. This one is sum of products form. That means first it's going to be 2 level. First level AND gate, the second level OR gate. And then the number of components and OR gates are going to be minimal. That is the minimal function related circuit. So that means minimal cost related circuit under the constraint of AND OR form. Okay. So we defined now minimal function. So we're going to find this minimal function now. Our aim is to find this minimal function. So what is this minimal function? There is another definition. It is called a reducible function. This definition might seem the same as the minimal function. So we've got to differentiate those two. Which one we're going to prefer, we've got to make the decision on that. How we're going to make the decision? You see here, this is a function. So this function underneath is the sum of product form of this. This is first canonical form. So if you want to draw the circuit corresponding to this one is going to be 1, 2, 3, 4, 5, 6. 6 AND gates. And the fan-in is going to be 3 variables each, isn't it? And 1 OR gate. Fan-in is going to be 6. OR gate fan-in is going to be 6. So that's the realization. So this is a reducible function. I'm going to define what it is. So if you do this one, once again it is sum of product form, so it's going to be 2 level. Then the number of AND gates is 4 AND gates we've got. And fan-in for the AND gates is just 2. Fan-in 2. And 1 OR gate. Fan-in of this OR gate is 3. So better than this one, isn't it? But when you come to this one, these two, these are all equivalent. So you can check this one is equivalent to this one is also equivalent to those two. How are you going to check it? Find the truth table for this one, find the truth table for this one, find the truth table this one and this one. You're going to see all of them the same. So this circuit corresponding to these two functions are 4 AND gates, so 3 AND gates, sorry, make it correction. 3 AND gates. Fan-in for these AND gates is 2. And 1 OR gate. And fan-in is 3. So I made a mistake here. Fan-in for this one, OR gate, 1, 2, 3, 4, isn't it? It should have been 4. So correct that one. It is 4. Fan-in. So if you compare those now, this is better than this one, but this is much better than this one. So these two are the minimal functions that we defined already. So this is the one that we are going to define right now. It is irreducible function. Now, I do the definition later on, but we see here, this seems that we've got to find the minimal functions, not the irreducible functions. So let me define what is irreducible function is. It is given here. It's going to be equivalent to the original function, so that is right. So G1 should be equivalent to a given f function. And then it says here, the product terms in these irreducible functions are the ones like that. If you remove any one of the variable in any product term, if the equivalency is not valid anymore, then this function is called irreducible function. Now let me explain it in another words. So if this is a irreducible function, which is equivalent to 1, if it is so, that means if you remove that x3, it's not going to be remove this, that means you're not going to say x3 anymore. That means you found another function. This function is not equivalent to f. Don't do this. Keep this x3 as it is and remove that x1 and see there is no equivalency. Remove this one, see no equivalency. This one, this one, this one, this one, this one, repeated 8 times. If at the end, if you say that the function that you found is not equivalent to the original given function, then this G1 function is called irreducible. That means you cannot remove any other variable from this function, right? Now, the other two functions here are the minimal functions. That means the number of product terms minimal and the number of variables in each product term is minimal. So if you look at those two, they are equivalent. Which one do you prefer? Irreducible one or this one? Of course, this minimal function we're going to prefer because the cost is minimal for this one, not for this one, because you use more AND gates here. Then conclusion is this. So you see here, minimal function is irreducible, but each irreducible function is not minimal. The opposite is not true. So this minimal function is irreducible. Why is that? Because if you remove one of the variable here, it is not equivalent to f anymore. Why is that? Because we said you're going to have minimal number of product terms. In each product terms, the number of variables should be minimal. When you remove it, if it is equivalent, then that means that is extra variable we've got here. It's not the minimal within this product term. Therefore, minimal functions are irreducible functions. But opposite is not true. Just by looking at this two, I can say that in the minimal function we've got minimal number of product terms. In here we don't have the minimal number of product terms. So conclusion, we've got to find the minimal functions, not the irreducible function, but these minimal functions that we're going to find are going to be irreducible as well. So if you find the irreducible function, not the minimal function, this is not the one that we are looking for. We are looking for minimal functions which are at the same time irreducible function. So another conclusion is this quite interesting. We've got two functions here equivalent to the original function and both of them minimal. So that means minimal function is not unique. There could be more than one minimal functions. Is there any benefit on that or not? We're going to see it later on. So let's come to the next step. We've got to introduce a new terminology which is called cover function and prime implicant. Now, what is the cover function? Let me read the definition here. If f function is 1, whenever h function is 1, then it is said that f covers h. So you could see it in this example. Now we've got an h function and f function. Now we are saying f covers h. Why is that? Because h is, whenever the h is 1, f is 1. H is 1 here, f is also 1. H is 1 here, f is also 1. H is 1 here, f is also 1. Then f covers the h. I'm not going to say same thing for the zeros. I'm only saying it's for the ones here. Then it said f covers h. Conclusion, any h function not covered by f, then h cannot be the minimal function of f. So that means minimal function should be covered with the original function. Wherever the minimal function is 1, the original function should also be 1. So that means I'm going to find a minimal function. This minimal function is going to be covered by f. I know this in my mind for the minimal function. Let's come to prime implicant now. Prime implicant, in Turkish it is called asal bileşen. Prime implicant is a product term and must be covered by f, and removal of any variable in P causes P is not covered by f, then f is said prime implicant. Let me explain it here. So the prime implicant is a product term, so it is a product term, so something like that, x1, x3 prime is going to be covered by f. So that means if you write this product term, so this product term is covered by f, isn't it? Any product term here is covered by f. Wherever this one, whatever the others are, your function is going to 1. So this product term is covered by f. Now it says this product term is called a prime implicant if you remove one of the variable here, it is not equivalent anymore. It is not covered by f. That means if it is so for all the other variables, all the variables in this product term, then it is called prime implicant. That means this. The number of variables in this product term is minimal. You cannot remove any of the variable in here because it won't be covered by f. In order to find the minimal function, I've got to write the product terms which are covered by f. I know that, isn't it? Because when this product term is 1, my minimal function is going to be 1 as well, because they should be equivalent. So the conclusion is quite interesting. Minimal function includes product terms which are prime implicants, asal bileşenler. So in order to find the minimal functions, we've got to find the prime implicants. It doesn't mean that that's the end of the process. No, we've got to find the prime implicants. That is the first step. Minimal functions product terms are minimal prime implicants. In other words, in order to find the minimal functions, prime implicants should be found. Each product term of this f function is a prime implicant. Now, as we said this in the previous one, this is a minimal function. If it is a minimal function, all these product terms are going to be prime implicants. Prime implicants, prime implicants. So that means if you remove this, this function won't be equivalent to the original function. Okay. The next step. Now we are going to try define now essential prime implicant. The previous one, it was the prime implicant. Now this is essential prime implicant. Now consider a function given to you, and this function has got a one value here. That means true min term included is none. For this row, function value is 1. If this one is covered by a product term, by a prime implicant, which is a product term, which is a prime implicant, and this one is not covered by any other prime implicant, from the other prime implicant, the other prime implicant does not cover this one. Only this prime implicant cover this one. What does this mean? If you write your minimal function which includes all the prime implicants apart from this, and write this f minimal as the summation of all these product terms except this one. Except this one, I said. So I could say that this minimal function is not equivalent to the original function, because this minimal function won't be equal to 1 for this row. Why is that? Because I said this prime implicance is a special prime implicance which covers this one only. The other prime implicance does not cover this one. So I gave a special name for this prime implicant, say that essential prime implicant, essential. In Turkish, temel asal bileşen. So conclusion is this. I've got to find all the prime implicants, and among those prime implicants I should find out essential prime implicants. So these essential prime implicants must be in the minimal function. It doesn't mean that essential minimal functions cover only the essential prime implicants. What is true is this: all the essential prime implicants must be in the minimal functions. What is the additional thing that you've got to do is this: we are going to find the essential prime implicants, and we are going to add the other prime implicants in such a way that minimal number of prime implicants should be added. When after this addition, my minimal function should be equivalent to the original function. So when you add minimal number of prime implicants, means you found the definition of the minimal function, because in the definition of the minimal function we said we're going to have the minimal number of product terms. Among these product terms, prime implicants must be in, and the other product terms, the number of product terms to be added should be minimal. That is the conclusion. So this tells me the method. When a truth table of a function given to us, that means input-output relations given to us, then we are going to find the prime implicants related for this function. The second step, we are going to find the essential prime implicants. And third step, we are going to find minimal number of prime implicants to be added to the essential prime implicants in order to get the minimal function. So we are going to explain these steps to you, on an example in the next video, not in this one. So that's the end of this video.